Hello, this is Math 140, day 17, and today we're going to talk about quadratics. That is the quadratic polynomials. They will give you functions and the connections to their graphs. The graphs are called parabolas. So start with the simplest one, the parabola. So it's the graph of y is x squared. And okay, you could sketch that, but I'm gonna already step a little bit away from that and make constant multiples of that. So that gets you to y is a times x squared. A could be any constant, non-zero constant. What does that look like? Just rough sketches. We start with the standard parabola, which I want to put in blue. So that's what we get when you have a equal to 1. And then when we make this number a bigger than 1, that means it's steeper. It goes up faster. So you get parabolas like this. Next thing, if you replace x by a negative x, we get the same function. So this one will have mirror symmetry with regard to the y-axis. So the left side looks just like the right side. And this is all when a is bigger than 1. Next, let's choose the number a between 0 and 1. It has to be greater than 0, but less than 1. Then we'll get something, well, that grows less fast, so it goes like that. Or even just like that, or very slowly. And it still has that mirror symmetry. And all of these are for a greater than 0, but less than 1. Now you could have the number a being negative. And that is an equation which you could also get when you take negative y is ax squared, where a is positive, which we've seen before gives you a flip about the x-axis. So let's do that in the same colors. Like that. Mirror symmetry. Like that. Stuff like that is happening. So that would be for the number a between -1 and 0. The standard parabola flipped gives you y is negative x squared. So that looked like something like this. And finally, a less than -1, that goes even steeper. I'm doing this live on camera so that you can see it grow. Of course, it's much nicer if you plot it with a computer, but now you've got it in sequence and you've got the voiceover, and it's still beautiful. Okay, so we got lots and lots of different parabolas, all from changing that single number a. But now we're going to extend that even further and do the shifts that we talked about last time. Horizontal and vertical shifts. So for example, y is 1/4 times x plus 3 quantity squared equal to, sorry, I meant to say y minus 1. Allow me to add plus 1 in the back. So what I meant to say was y minus 1 is 1/4 times x plus 3 quantity squared. Either way, describes the same points in the plane as a graph. What does the graph of this function look like? I would start with y is 1/4 x squared. So that's one of those green thingies. Goes up slowly. Something like this. And if if x is 1, then y is 0. Oh, if you're talking about y is 1/4 x squared. There, if x is 1 or negative 1, then y is 1. So let me sketch that. Those would have to be my units on x and y axis, not the same units. And now we can shift the whole thing by 3 units. Where? To the left. Because we think back to x minus a. If you replace x by x minus a, it shifts the x-axis a units to the left, and therefore the graph gets shifted a units to the right. Here we're shifting x to the x-axis to the right, so the graph gets shifted by 3 units to the left. So we better make a new sketch here. That green graph gets shifted over, and it's now touching the x-axis when x is -3. I'm going to go it white. And it looks like this now. Far out left. Y is 1/4 times x plus 3 quantity squared. For example, if x is -1, then y would be 1. This is how far we shifted this whole thing. 3 units to the left. And finally, to get back to our original functions, y minus 1 is 1/4 times x plus 3 quantity squared. I need to shift the whole thing up by 1 unit. Up by 1 unit. And that is the graph of the function that I sketched first, that I wrote about first. Still rises slowly, but it was shifted up by 1 unit. Okay. Y is 1/4 times x plus 3 quantity squared plus 1. Or you write the plus 1 on the right-hand side, not next to the y. Plus 1. Okay, so we can shift those parabolas, the colorful parabolas that I had earlier, here, everywhere, left, right, up, down. And what we get? We get the graphs of all quadratic functions, all of them. So with constant multiples and the horizontal, the vertical shifts, we get graphs of all quadratic functions. Because if you have a quadratic function, y is a x squared plus bx plus c. That's a quadratic function, okay, by definition. With a non-zero, you can factor out the a, brute force, x squared plus b over a times x plus c over a. And they can work on the parentheses and do completing the square. And rewrite that as x plus, sorry, minus, I want minus some number that I want to call p quantity squared, and then some other number q. With completing square, we can always do that. I want to write down the p that we need to choose here. That would have to be the opposite of b over a divided by 2, half of b over a. I say times 1/2. So negative b over 2 times a. Keep that in mind. And then there's a way to figure out the q from there. We've done enough completing the square. I want to jump in right there when this parabola is already written in this convenient form. The quadratic function is already written in this convenient form, because we can read off the shifts. What are the shifts that take the standard parabola with a constant multiple a to this function? Standard parabola with this constant multiple. So we have y is x, a times x squared, and then shift p units to the right and q units up. Which means if p happens to be a negative number, then you need to shift to the left. That was what my example did when p was -3. That's why I made that p a negative number. And the other one, the q, again, if q is positive, it's a shift up. If q is negative, it's a shift down, because I wrote the q on the side of the x, not on the side of the y. Okay, let's do one more example for that. Maybe go the other way. Given the graph of y is x minus p quantity squared plus q is something like this. And I've marked one special point. That point, x coordinate is 1, y coordinate is -2. What shift do we need? What values of p and q do we need to get this graph? And the answer is p should be 1 and the q should be -2. In other words, you can just read them right off the picture. So this is like a graph of the standard parabola shifted 1 unit to the right and 2 units down. That's all there is to it. Standard parabola, 1 unit right, 2 down. Because it said -2, I have to shift 2 units down. And then, like last example, I can change that up a little bit. Given a graph with 3 points on it, again with a special point, but now I'm telling you more. The graph passes through those 3 points and it still looks like a parabola. Like that. Find a quadratic function. So the graph passes through those 3 points. So what's the same as in the last example? It's that special point 1, x coordinate 1, y coordinate -2. And to get to there, you've got to have the same shape. So y is x minus 1 quantity squared minus 2. Hope I said, yeah, minus 2 earlier, just like before. But now we also want to pass through those other points. So when x is 5, we want to get y is 0. When x is -3, we want to get y is 0. And we can achieve that by having this wonderful extra number a. And it's up to us if we choose to have parentheses around the whole thing or have the a just multiply the x minus 1 squared. So let's do it like this. So that gives me additional leeway and it allows me to adapt the function to fit this graph. So we're given y is 0 when x is 5. And that allows me to find a. That's 4 squared is 16. So 0 is 8 times 16 minus 2, which means a has to be 1/8. And you can check when x is then -3, yeah, we also get 0 for y. Okay, so the function is y equal to 1/8 quantity x minus 1 quantity squared minus 2. Not there by allowing this constant multiple out front.